Great. Well, good evening, everybody, and welcome to Crawley for our talk this evening on why weather forecasting has improved. We are welcoming Bob Ridaway to come and speak to us tonight. Now, Bob has a PhD in meteorology. He was pronounced it better than me, from Edinburgh University, and a long career at the Met Office, where he was, among other things, head of the London Weather Centre, head of training, head of development, resourcing and technology. He's also done a lot of work with the Royal Meteorological Society, of which he was the General Secretary for 8 years, I think. And he was recently the President of the European Meteorological Society for 3 years. That's the background to Bob that I have here on my piece of paper. So with that, I will hand over to Bob for the talk, and I'll speak to you again later.
Oh. Right, well, thank you very much for inviting me to give a talk to you. As I was sitting at the back there, I was just thinking about when was the last time I was amongst so many engineers. And I realised it's when I was at university and in the men's union, had a bar, it was always full of engineers. So the answer to this question, why have weather forecasts improved, there's a short answer to that, and that is because of you, people like you. But also there's a longer answer, which I will give you now. Let me just tell you a little bit more about me. You know, life and careers often like what we experience in meteorology. You'll see later when we do forecasting, just a very small change can happen, have a massive effect later on. And the reason I'm here talking to you today is because something like that happened to me when I was 15. So when I was 15, coming up to O-levels, you remember those? Our geography teacher had a friend who worked for the British Antarctic Survey. Now at that time, I should say, I was fascinated by history, and I thought I'd go to university and study history. That's what I wanted to do. But we had the geography class, and this man talks about Antarctica, and I can still remember some of those slides he showed us. It's just amazing. And so at the end of the lesson, I asked my geography teacher, who goes to Antarctica? And he said, I think meteorologists do. So I wrote to the Met Office and said, what do I need to do to become a meteorologist? And they said, go to university, study maths or physics, and join the Met Office and we teach you the meteorology. And so that's what I did. So my whole career depended on that answer from my geography teacher. If he said, I don't know, I'd probably be a historian. I wouldn't be here in front of you. So why have weather forecasts improved? As you probably realise, that's why I'm talking to you, is technology has just had an enormous impact on the improvement of weather forecasts. And I want to tell you about that. So where to start? Well, of course, some time ago when we had, I suppose, quite crude technology like barometers and thermometers, but the big development happened after the invention of the telegraph in 1840 or thereabouts, which I gather is sort of the start of your institution that was involved in telegraph operators. And that was very important. You see, before that, when it came to forecasting the weather, the only weather information you had is what you could see out of the window. You didn't know what's happening anywhere else. And with the telegraph, for the first time, you could collect observations from other parts of the country, which meant you had some idea of what was going on, and you could start to make weather forecasts. And it was in 1854 that this gentleman here, Robert Fitzroy, became head of an organisation in London, which eventually became the Met Office. It wasn't called that, but it's the start of the Met Office. And so he is known as the founder of the Met Office, although he's renowned for something else. And that is, Robert Fitzroy was the captain of the Beagle, who went around the world with Darwin. And that's, so he was a very fine sailor, a very experienced sailor, very interested in the weather, and became head of this organisation, the Met Office. And what they could do, now this is what the Met Office, they could collect observations from around the country by the telegraph, which they could make weather forecasts. And this, on that side, is the first ever public weather forecast. It's published in the Times. You see, it's not a great detail, so because the writing is very small, I've just written some of the things there. So probably during the next 2 days, north, moderate, westerly wind fine. So not a very detailed weather forecast, but it was a start. Then after that, there was some further developments, and not only was the telegraph, I should say, in the UK set up, but also the telegraph meant that you could get observations from other parts of the world as well. So you had a wide range of observations available. And in the early part of the 20th century, that led to a very important conceptual change in meteorology. And that's fronts. Now, when you look at a weather chart today, you see it on the television, you see fronts, warm fronts, cold fronts, occluded fronts. They're there, they move, they're very important to understand the weather. Well, it's only when they started to be able to collect observations together that fronts were discovered. And that was in the early part of the 20th century. By some Norwegians. So that was very important from the point of view of weather forecasting, because if you could identify where the fronts are, then you had some idea what's going to happen next, because they have a life cycle. There's some predictability about them. Another very important development in the 1930s, technology development, was the development of what's called the radio sonde. A radio sonde is a balloon filled with hydrogen or helium, and you attach instruments to it which measure the pressure, the temperature, and the humidity as it goes through the atmosphere. So for the first time, you could find out about the whole structure of the atmosphere. It's a very important development. And that's how people forecast the weather. They had these observations from the land, which were transmitted by telegraph. They had the radio sonde information. And weather forecasting, well, it's probably fair to say it was still more of an art rather than a science. And probably the ultimate example of using this traditional technique of weather forecasting was the D-Day forecast, which was celebrated quite recently, it's in June of this year. And on the side there, it's got the requirements there had to be for the D-Day landing, which are really very restrictive. And it was very important that they were satisfied. And it was planned to have the invasion on the 5th of June, 1944. But on the 4th of June, the meteorologist attached to Eisenhower, this man, James Stagg, was given the task of advising Eisenhower about whether they should go ahead with the landing on the 5th of June. But the weather looked as if it just wasn't possible. Now that was a bit of a concern, because if they didn't do the landing, the D-landing, round about that time, they'd have to wait another 2 weeks for conditions to be right, about moonlit night and low tide at dawn. So there's a lot of pressure to try to decide when they could go. And Stagg noticed on the 5th of June that there's an observation in the Atlantic which showed some rising pressure where they hadn't expected the pressure to be rising. And rising pressure is an indication of sort of an anticyclone or a ridge which is associated with some good weather. And he thought that on the 6th of June there would just be a break in the weather which would justify the invasion going ahead. And that's a tough call. But he did it. He advised the Supreme Commander, and they went ahead on the 6th of June. The weather was actually worse than they were forecasting, but it wasn't so bad that it spoiled the landing. So that was sort of, I suppose, the ultimate example of this sort of traditional way of doing weather forecast. Some observations, just a lot of knowledge about what's happened in the past, recognising patterns. To go then to the modern era of weather forecasting, we have to go back now to the beginning of the 20th century. This man, Wilhelm Bjerknes, who was a Norwegian meteorologist, and he wrote an article, published a paper, which he said, look, if we know the state of the atmosphere, we've got lots of observations, if we know the state of the atmosphere, and we recognise that the atmosphere is just a complicated fluid, it's just a fluid, and we know the physical laws that describe behaviour of fluid, Newton's second law of motion, the second law of thermodynamics, just classical physical equations. He said, surely we can use those to predict the future, predict what the weather's going to be. And so that was just looking to the future. Couldn't do it, but that set someone thinking. This gentleman called Louis Fry Richardson, and he was someone working in the Met Office before the war, and he started thinking about this. How can we forecast the weather by numerical process, by using the laws of physics? And he started thinking about it, and then the First World War started. He was a Quaker, and so he didn't fight in the war, but he was an ambulance driver. And whilst he was doing that, he decided to actually make a forecast using numerical process. It's a paper and pencil is how he did it. It took him 6 months to do it, to do a 6-hour forecast of this point here. And the forecast was absolute nonsense. It was predicting a rise in pressure, which was just impossible. It's because he didn't actually know, or nobody knew very much about the numerical methods required to solve these differential equations. But he wrote a book about it in 1922, outlining in principle how you could forecast the weather using the laws of physics. But it wasn't actually possible to do it in any meaningful way until they had computers. And it was in 1950, was the first computer forecast. It was done in America. It was using the computer that was built for the atomic bomb project. It's 1950. And it was a very simple model of the atmosphere. It assumed the atmosphere was just one level, only one layer in the atmosphere, and the horizontal grid was about 450 kilometers. So it was a very crude model. But they did it. They showed that in principle you could sort of simplify the equations in a meaningful way and produce a numerical forecast. Well, it was very revealing, I thought, this. The people on that side over there are the scientists, and the people who are doing all the work with the equipment are the ladies there. These things happened in those days. So that was the first numerical forecast that was done. So we're going to come back to how you do a forecast in a moment, because before you do any kind of forecast, you've got to have the observations. You've got to know the state of the atmosphere. So now we just look at the observation side, and we'll come back to how we use those observations. And this is just an indication of just a whole range of observation types that are available nowadays due to technological advances. I'm going to tell you a bit more about this. in a moment. So we have satellites, and I'll tell you about how they, the sort of information they provide. Have aircraft, they provide information about the temperature and wind. You have these are the radio sondes going up. We have ships making observations. We have drifting buoys that send information. We have the observations on land, what used to be called the Simpson screen. I expect you had one at school. They're not called that anymore, they're called thermometer screens. And we have radar as well. And so these technological advances, these observing systems, have just transformed what we know about the atmosphere and or the state of the atmosphere. I want to tell you a bit more about some of those. So the first one is the radar. So with the radar, over here, this is the current radar network in the UK. So you have these radars, but you actually put the information from the radars together so you get a complete coverage. And you see the result of that on the television. You see the television forecast. Often it says this is the radar. You see. And what the radar is doing? Well, the idea is that you send out a beam of, you have a radar, microwave, and it hits raindrops, right? And you get backscattering from the raindrops. And the bigger the raindrop, the more backscattering you get. And the bigger the raindrop, the heavier the rain. And so by measuring the backscatter that you get from the radar, you can determine something about how heavy the rainfall is. But then the radars got more sophisticated. And so nowadays, there's two extra things. They have dual polarization radars. So the polarization is both horizontal and vertical. That tells you something about the shape of the drops that are doing the backscattering. That allows you to differentiate between rain and sleet and snow, which you couldn't with just normal radar. And more recently, they've introduced Doppler radars, and that what that tells you, you send out the signal, it hits the rain, and if the rain is moving towards you, the frequency of the backscattering increases. If the rain is moving away from you, then the frequency decreases. So you can actually use the radar to tell you something about the wind direction. And this is something that I just took it when I was putting the presentation together. It was just the radar observation at a particular time on that day. But there are problems in using the radar. On the other side, just to give you an example, so on the top one, what's happening is that the cloud is some distance away, which is raining, but the radar doesn't see the rain. It sees the cloud, and as far as the radar is concerned, there's no rain, but there is. So you get an incorrect signal. The second one is where the radar picks up the rain, but the rain is evaporated before it hits the ground. So the radar is saying there is rain, but in reality, there isn't any. Another problem is the bottom slide, and that is, probably remember from your days doing geography, precipitation is enhanced when you go, when there's high ground. The air is forced up over the ground, then you get more rain. And so in the bottom one is a case where the radar is picking up the rain high up, that's fine, but the rain is increased because of the effect of the mountains there. But he doesn't know about that. And so the actual rainfall is underestimated. So radar is really very important, but it's not perfect. But probably the biggest impact on the weather forecast from the point of observations is the use of satellites. And in meteorology, there are two kinds of satellites that are used. One is called the polar orbiting satellite. The polar orbiting satellite, as the name suggests, goes over the poles. So it goes over the poles, and the Earth rotates underneath the radar. And so it looks just as a small swathe of the atmosphere of the Earth as it goes underneath. And typically it takes about 100 minutes to go right around the Earth. And they are typically about 850 kilometers above the ground. The other kind of satellite is called a geostationary satellite. And the geostationary satellite sits over the equator. And that has a period of 24 hours. So what it means is it's always looking at the same part of the Earth's disk. And I'll show you in a moment why that is important. So with these satellites, there's lots of them. And so I tried to find out exactly how many there are nowadays, and it keeps changing. But there's vast numbers of these. And so, for instance, with the geostationary satellite, isn't just one there. There's lots of them scattered around the world by the Americans, the Russians, the Indians, the Japanese. They're all putting these satellites up there. It's the same with the polar orbiting one, or that these countries are putting up their own polar orbiting satellites. And this is just an indication of how important these satellite observations are. So this is simulated data, it's just the data that is used to produce a weather forecast. And you see the infrared sensors, the information about infrared, I'll come on to that in a moment, and microwave sensors are by far the biggest contributor of data to understanding the state of the atmosphere. The atmospheric motion vectors, well, they come from the geostationary satellite, because what happens, the geostationary satellite, they always look at the same bit of the atmosphere, the same bit of the Earth, and they look at clouds. And you look at clouds at one time, 15 minutes later, you try to see where that cloud has moved to. And they moved, and if they moved, you assume that's because the wind was blown. And so by looking at the movement of clouds, you can deduce the wind at that level. How do you know what level it is? Well, that is because you know from the infrared radiation, you have an estimate of the temperature of the cloud top, which gives you some idea of where it is, the top of the cloud is in the atmosphere. And so you get these, they're called atmospheric motion vectors. So it's winds. I'll tell you more about radio occultation in a moment. The wind LiDAR, that's ones where the satellite is, there's two kinds of satellites, one which are passive, which just look at the radiation which is coming up from the Earth and the atmosphere. Also, there's some active ones. And the wind LiDAR is an active one. So this is a satellite which sends down a beam of ultraviolet light, which gets scattered by the aerosols in the atmosphere. And that scattering can be used to give you some information about the wind. I mentioned aircraft. They measure the wind and temperature as they go along, but also they tell you about the structure of the atmosphere, because they can tell you, especially about the temperature, as they're taking off and going through the atmosphere. They're always recording the temperature. That information is made available. So it's like finding a profile through the atmosphere, and it tells you what the temperature is. You notice lots of aircraft. The radio sondes, see, already mentioned, and the others are mainly the land observations. Now, I'm not expecting to see the detail of this, but it's important to see how the satellites add to the information about the atmosphere. So at the top, we've got the surface observations. So there's lots of them if you're over land and if you're not in Africa. Radio sondes, right? They're quite expensive to let off. And so there's far fewer radio sondes let off than surface observations. But you see, it's very scattered. Hardly any over the oceans, and big sparse areas of Africa and South America. But aircraft, lots of aircraft. This is observations in a 6-hour period. So you see there's a big gaps in the observing network, and that's where the satellites come in. So the infrared sounder, that's a satellite which looks at the infrared radiation coming from the atmosphere in different wavelengths. And from that, you can deduce the temperature structure, the humidity structure of the atmosphere. I've just showed an example. That's the sounding from just one satellite. And I just thought it's interesting seeing that when you go from what's happening in reality, what it looks like on a chart, that's what it looks like. But in reality, there's loads of these satellites doing the infrared sounding. And there's another set of satellites, or often it's the same satellite, but sometimes some satellites have both instruments on, to measure infrared and humidity. And these satellites look at the microwaves coming from the surface of the Earth and the atmosphere. And that tells you something about the humidity in the atmosphere. I mentioned the atmospheric motion vectors. And then there's these two, which I'm going to tell you a bit more in a moment. The GPS, Global Positioning System, and the scatterometer. So first of all, the GPS radio. This is a relatively new way of getting information about what's going on in the atmosphere. So there we've got the satellite sending out a signal. And because the signal goes through the Earth's atmosphere, then it gets bent, right? Because of the temperature and humidity in the atmosphere, or the water vapor, the signal doesn't travel in a straight line. And so you can deduce something about the refractive index. And if you can work out so the signal is then picked up by another satellite here. So it's this bending of the signal tells you something about the atmosphere that the signals pass through. And from that, using a lot of clever mathematics, you can work out something about the vertical profiles of temperature, pressure, and water vapor, and the electric, can't even read it. So that's a new form of information. And also have a scatterometer. Now, scatterometer, this is active profiling. And so it's a satellite which sends out a beam of microwaves. And the microwaves get scattered of waves in the ocean. Not the big waves, but the little waves which have a wavelength of something like 5 to 20 centimeters. Those are the little waves on top of the big waves. And those waves tend to be caused by the wind. And so by looking at the scattering from this, and what they typically have is they look in 3 different directions and get the scattering. And from that, you can deduce the wind at the surface. Clever stuff. So nowadays, there are lots and lots of observations that are available. And one of the things that you have to do is then get them into your model. So what is this model? So a bit more about that. You think of the model, you create a 3-dimensional grid. that covers the whole of the atmosphere. And what you want to do is determine the pressure, temperature, and wind at each grid point. And so you use all these observations, different types of observations, to work out what that's going to be. These key parameters, pressure, temperature, wind, and humidity at each of these points. And then the model, there's two parts to it. One is what you think of as being the dynamics. And that is, the dynamic bit is what happens because the wind is blowing, it's moving things around. All right, that's the dynamics. But there's lots of other things happening in the atmosphere. It's not, the pressure, temperature, and humidity at a point don't just change because the wind is blowing or there's vertical motion. There's all sorts of other physical processes going on in the atmosphere. And so these are just some of the physical processes which are going on in the atmosphere. Like there's the radiation from the sun, shortwave radiation. Some of that is reflected off clouds. Some is reflected off the Earth's surface. There's long-wave radiation coming from both the surface and the atmosphere and clouds. You have precipitation forming. You've got clouds, you've got precipitation. You have these convection, things like thunderstorms. And you've got the transfer of heat and moisture from the surface, from the ocean to the atmosphere. And the same over land, you have the transfer of heat to the atmosphere. And all those processes you've got to incorporate into your model. So the model is both the dynamics bit, which is the really easy bit, but then all these physical processes you have to try to represent. And that is quite a challenge because some of these processes happen on a very small scale, on a smaller scale than the grid that you're using. And so you have to do what's called parameterization. You have to try to describe these sub-grid scale processes in terms of the grid scale parameters that you have. And that's called parameterization. So representing the physics, the physical processes, is really quite a challenge. It takes a lot of time in these models. So, how have things changed? So, using the computer, using a numerical model, the Met Office in the UK produced its first numerical weather forecast, issued to the forecasters, probably operational, in 1965. It was only then that the computers were powerful enough to actually be able to produce a useful forecast. But it was a very simple model. It only had 3 levels, which isn't really very much to represent the whole of the atmosphere, you think about that. And the horizontal resolution was 300 kilometers. Very crude, as you'll see, compared with what happens nowadays. And I just mentioned the speed of it. You probably have to remember these numbers for when we see the next slide. But the memory, say, is 12,000 numbers and 60,000 operations per second. So that was the start. And this is nowadays. So this is the numerical model that's used nowadays. Has a global model. We look at the deterministic forecast. I'll say something else about this model in a moment. But the deterministic forecast has a resolution of about 10 kilometers over the globe and has 70 levels on it. And they produce a forecast every 12 hours for the whole of the globe. And the way in which you do the forecast is that from these equations that I mentioned, Newton's second law of motion, the second law of thermodynamics, those laws tell you about the rate of change of things. So Newton's law tells you about the rate of change of velocity. The second law of thermodynamics tells you about the rate of change of temperature. So what you do, you have the grid, you've calculated, this is the start, the pressure, temperature, humidity, the wind at each of the grid points, And you now calculate the right-hand side of these equations, all the things which are going to cause the temperature change. Just stick with the temperature. And you do that for the velocity and the humidity. And then you assume that the rate of change of temperature stays the same over a short period of time. So you can calculate the temperature sometime, a short time in the future. And in the global model, this top one, I looked it up today, it's 4 minutes. So the time step is 4 minutes. So in the global model, you make a 4-minute forecast. You calculate all the physical processes and the dynamics, this vast amount of calculations, calculate the rate of change of temperature again, and do another 4-minute forecast. The other one that's mentioned there is just a fine mesh forecast which covers the UK area and a bit of the continent and the Atlantic. And there, it's a 1.5 kilometre grid length, so it's very fine, 70 levels in the atmosphere, and there the time step is 100 seconds. So you do a 100-second forecast, do all the calculations again, do another 100-second forecast, and you build up a forecast in that way. I'll tell you a bit more about the ensembles in a moment. And so these forecasting systems, enormous amount of research and development's gone into it. It's over 1 million lines of code. And the Met Office is using 205 billion weather observations per day. That's because of all these satellite information coming at us. It's mainly. And I don't know if you remember the sort of numbers that they had before with regard to the computer, but these are just huge numbers with regard to the power of the computers nowadays. Now, this ensemble forecast. Now, this is something important, an important development. So, when you do a numerical forecast, you need to do it in a certain time, right? Because the forecasts are there for a purpose. You want to use the information. And so the forecast, using the computer, simulating all this data, manipulating the data, doing the forecast, you've got to do it within about 2 hours of starting the process to make it useful. So there's 2 strategies you can use. So you've got, say, 2 hours, that's the time I've got. And for that 2 hours, what you can do is use the best computer model, the best numerical model you have, got the smallest grid length you can have, the most sophisticated physics that's going to do the calculations in this 2-hour window. And that's what they call deterministic forecast. That's a one-off. That is our very best we can do. That's our best model. But there's another approach you can take, and that is you say, well, we're not going to just do one forecast. We're going to do lots of forecasts. We're going to do an ensemble of forecasts. And the ensemble forecast, you have to use a different grid length, a larger grid length, and which is mentioned here. But the question is, why do you want to do ensemble forecasts? Well, that's all due to what's discovered by this gentleman, Ed Lorenz. And it's quite interesting how he's discovered chaos, as it's called. And what he was doing, he's American, worked at the Massachusetts Institute of Technology. He's interested in weather forecasting, not weather forecasts, the sort of equations you use for weather forecasting. And he created from these equations you use for numerical weather forecasting, a slimmed down version of those equations, very simple, but retain the real essence of it. So he wasn't trying to make a forecast, he's interested in how these equations behave. And so he used these and he ran, we call it a forecast, but it's not trying to forecast the weather. It's how the solutions of this set of equations varied in time. And he must have printed out results at various times, right? And so then he decided to do the simulation again, but he didn't want to start at the beginning. He wanted to use the printout that he had. So from sort of halfway through this forecast. And so he typed into his model all these numbers which have been printed out on a computer, printed out. He just keyed them all in again and expected what happened then to be exactly the same as it was before. But it wasn't. Completely different. And the reason was in the computer, the numbers were stored to 6 decimal places, but when he printed it out, it was 3 decimal places. And what he found is that just very small changes in the initial conditions with these equations, like those using numerical weather prediction, can have a big impact on what happens in the future when you do a forecast. And that's chaos. People know about chaos, but it's due to a meteorologist. I'm sorry, I inadvertently covered up the word there. So what you've got to recognise is that observations are never exact. Right? All measurements have errors associated with them. So you never know the state of the atmosphere completely. With regard to the models, they're never perfect. You have to make all sorts of assumptions to have the model. And that means there's going to be a limit to what you can predict. And people often talk about the butterfly effect, which I've enough a bit of it inadvertently. And this was a statement in a paper written by Ed Lorenz. It's a butterfly that beats its wings in one corner of the globe and with a single action changes the weather halfway across the world. It's just saying that, in fact, a butterfly wouldn't have that effect, but really saying it's just a small change can have consequences a long way from where that happens. And so that idea is used with ensembles. So with an ensemble, instead of just doing one forecast with your best possible model, you do a lot of forecasts with a not such good model, with a bigger grid length. And so you start from different analyses, all of which are consistent with the observations, but each of the analyses to start with just slightly different. And then you run a forecast. So you have these members. And go back for a moment. So in the UK, for the global one, there's 36 members. So you run 36 forecasts with a 20-kilometre grid as opposed to the 10-kilometre grid for the deterministic forecast. And what you then do is look at how alike or unlike these forecasts are at the end of it. Now, if you do that, if all the members, the forecasts, if they're all essentially the same, then you have some confidence that the atmosphere is relatively predictable. But if they have lots of different solutions, very variable, it means from a forecaster's point of view, you have to be very careful in saying what's going to happen in the future. So often in the weather forecast, there's one quite recently where the forecaster was talking about a low, and he's saying, but we're not quite sure where it's going to move to. And that's because the ensembles must have shown lots of different tracks of that low, so they couldn't be certain about it. And so these ensembles have become very important because it illustrates the unpredictable aspects of the atmosphere.
Can you just say again, what are the different inputs to all these different ensemble forecasts?
Well, it's exactly the same observations, right?
Yes.
The observation is exactly the same. But when you determine what the values are going to be at these various grid points, right, which is the starting point, those starting points are just slightly different. Because what you're doing, you're taking account of the fact that the observation is not perfect, they all have errors, or you assume You have to assume an error. And so you use that to produce the analysis. So all the analyses are slightly different. They're all consistent with the observations, but all the analysis is just slightly different.
Different levels of accuracy, is that feeding into the observations? Or
Well,
3 or 6 decimal points or something?
no, so when you do the analysis for the deterministic forecast, you go through this process of analysing all the observations, and in doing that, you do take account of the fact that there are errors in the observations. And, but you have to make an assumption about what the error is going to be in this particular case. Now, when you do it again for this ensemble, you assume that the error is taken from the error profile of those observations. You pick something there. So it's consistent with the observation and the error that you have. Right. And so what you then get is set forecast. Now this isn't from the Met Office, so they don't seem to make readily available their ensemble. I don't actually see it, just to illustrate it. This is from the European Centre for Medium Range Weather Forecasting, which is an international organisation based in Reading. It's coming together. They do medium range forecasts more than 10 days, up to 10 days and beyond, and funded by a lot of European countries. That's to do with the EC. It's just a separate meteorological organisation. And they use 51 members of the ensemble. And this is, so I'm not expecting you to be able to read it, it's just illustration of what a forecaster will look at. You look at these 51 members of the ensemble. But not just that, that's very difficult to analyse that. What they then do by pattern recognition, they try to group these ensembles into different scenarios. And so the forecasts then from this set of ensembles get given a couple of scenarios. Sometimes just one scenario because all the ensembles are saying the same thing. But sometimes there's 2 or 3 different sort of possibilities there. So they don't necessarily, well, they don't look at that, that's too much. So you try to group them together. And this is called a meteogram. And this is just showing here the cloud cover, precipitation, wind speed, and temperature. And these vertical lines just show the different values coming from the ensemble. So it's just indicating the variation you get from the ensemble. So, have the forecasts got better? Well, they have, I think, because of the observations, mainly satellite observations, and the computer models getting better and better, more sophisticated, because of the increase in computer power. And this is a measure which is frequently used. What it is doesn't really matter. It's a statistical measure of the accuracy of the forecast at a particular level. And this shows over time how the accuracy has changed. And a value of 60% is considered to be useful. And you see the 7-day forecast in 1981 when this is from the European Centre. The European Centre started was of no value at all, but now it's nearly highly accurate. And just in general, what they say over time is that you gain about 1 day in usefulness every 10 years. And that's really quite remarkable. That's the satellites and computers, and also a greater knowledge of the atmosphere. So, will it continue getting better? And the answer is, well, yes. I have no reason to think it won't. because there are more and more satellites being put up, measuring more and more different things. Just the technology is just amazing how it changes. And people want the satellites there not just for weather forecasting, but to monitor the atmosphere because of climate change. People want to know what's happening in the atmosphere. And so a lot of the satellites put up is for a monitoring purpose, but they're also used to help forecast the weather. Computers are going to carry on getting faster and more powerful. It's going to stop someday. It's the moment that happens. And so the computer models will have finer and finer grid lengths. The physics, these physical processes, the way in which they're replicated in models will get more and more sophisticated as well. And then the big, well, I'm going to say unknown, it's less unknown now, there's machine learning. What's the role of artificial intelligence? Well, machine learning. And there have been some experiments carried out at the European Centre, and they found that the forecast based on machine learning, by some statistics, is as good as those which come out of the computer model. Now, there's more to it than that. That's the sort of headline. There's more to it in that what comes out of the machine learning system is rather smooth, right? It doesn't have very deep things or sharp gradients. And with the statistics you use to compare forecasts, you find a smooth forecast actually does quite well in statistics. And so that's one thing. So it's really hiding away something. And the second thing is that even though the machine learning might be good at predicting the flow at 500 millibars, which is halfway up the atmosphere, it doesn't predict where it's going to rain. Right? It just does it with patterns. And so machine learning is going to have an impact. I think one of the immediate impacts, and the Met Office started to do this, is that weather forecasters have access to loads of information. They have all the satellite information, masses of satellite information. They see it on their screens. They have the radar. They have not just one model. They have the model from America, from France, from Germany, from the European Centre, all producing forecasts. And somehow, and they've got the satellite, they've got the radars, somehow they've got to make sense of all this data. And where you can see machine learning coming into that is showing or indicating to the forecaster, these are the things you should be looking at. Of all this data, these are the ones that are important. It's still for you to decide what it's going to be, but using machine learning to help the forecaster rather than try to replace the forecaster. Although I suspect eventually even the forecasters will disappear as well. So, to answer the question once again, why the forecast improved? Well, it's because of the technology, because of people like you. Is it going to continue improving? And the answer is yes.
Well, thank you very much. I found that very interesting, and I hope you guys did too. Do we have any questions for Bob? So, you tell me what the question is, I'll repeat it.
Can you elaborate on how that accuracy is measured?
Can you elaborate on how the accuracy is measured?
What it is, yeah. So these percentages are something called the anomaly correlation, right? So the anomaly correlation is that you compare the forecast, say, at 5 days, say, at a particular level in the atmosphere, say 500 millibars, but halfway up the atmosphere. You compare that forecast, you take that forecast and you subtract from it the climatology, and that gives you the anomaly. So the anomaly is the difference from climatology. And that gives you the anomaly correlation. And that is the measure that is used.
What variables did they compare? Is it just pressure?
Well, for this one, it's just a anomaly correlation, which is the height of the 500 millibar surface in the atmosphere. But they do this for lots of different levels. The reason I've chosen that one is because that is one of the key measures for the European Centre, which is where this comes from, which they have to say each year, or display each year, to show that their forecasts are getting better. So, but there's lots of different metrics like that. That is just one of them.
There was another question. Yes?
How does our forecasting compare to forecasting of other countries?
How does our forecasting compare to the forecasting of other countries?
Well, there's two ways of answering that question. So if the question is, how do the forecasts that you see on the television compare to other countries, the answer is, don't know. Because the comparisons which are done are with the model forecasts. And so by using statistics like this, which measure the accuracy of the forecast, there's a set of statistics which are used all around the world for assessing the accuracy of the forecast. And that is available, so you can do international comparisons. And what tends to happen is that which is best goes up and down, because it depends who's got the latest supercomputer. Right? You've got the latest supercomputer, you improve your model, and you do better than everyone else until the next country gets the new supercomputer, and they have a better model, and they do better. The only one which is consistently better is this European Centre. And the reason for that is that the European Centre, it's mainly there to do 10-day forecasts, all right? Not short-term forecasts, not over the next day or two. Although they have to do that, of course, to get to 10 days. And so the European Centre takes much more time to collect observations, because it's interested in the medium range. And so instead of fitting the assimilation of the data and producing the forecast into a couple of hours, they can take 6 hours to do that. They can collect more observations because they're really interested in the 10-day forecast, not the short-range forecast. So when they do these comparisons, the European Centre tends to come out on top. But for the others, it depends who's got the latest supercomputer.
Mike?
Do all countries have access to the same amount of data?
Well,
Do all countries have access to the same amount?
That's a very good question, because one of the things which makes meteorology quite special is the international cooperation. And that started in 1873. In 1873, they established the International Meteorological Organization. And that was established to support the exchange of data. And because if you're going to exchange data, which is crucial, you could do it by telegraph, you've got to have a code for doing that. You've got to agree on how you're going to code the observations that you're going to send. And so that's why the International Meteorological Organization was set up, was to have standards for the sharing of observations. And that has carried on. And every country realizes that our observations by ourselves, for our country, without everyone else's, of no use at all. So we share them.
Mike again.
A follow-on question. Looking at the accuracy of the southern hemisphere is nearly always below the northern hemisphere, but it suddenly gets better.
Yes.
Around
So,
about 2000 to 2000.
yeah, I should have mentioned that. And the reason is satellites, satellite coverage. And so early on, they didn't have the same satellite coverage, and it's the areas that benefit most from more satellites is sparse data areas. and it's the southern oceans where originally there were very few observations, and the satellites now fill that in, and so now there's no significant difference between the northern and southern hemisphere with regard to the accuracy.
We have another question.
Hi, yes. In your earlier slides, you showed that there seems to be a lack of data coming from Africa and
Yes.
in some cases from South America.
Yes.
Is that for commercial reasons?
No, it's just well, it's, two reasons. One is making observations is quite expensive. So when I worked in the Met Office, when you had surface observations being made, it's an observation every hour, right, which is typically what was done, you need to employ 6 people to do that, to continue with a 1 hour coverage. And so that is very expensive in manpower, and many countries can't afford to do that. With regards to radio sondes, they're quite expensive, and you require people to do that. Now, for both those, for radio sondes and the surface observations, you can automate those. And in the UK, nearly all the observing is done using automated systems, but they're expensive. And the countries in Africa and South America, some South America, don't have the wherewithal to either pay people to do it or invest in equipment to do it.
Another question, Mike.
Yeah, okay. Going back to the ensemble forecast.
Yes,
If you're in the UK Met Office
yes.
and you're doing all these ensembles, are they just for grids within the UK, or do you overlap a bit with, say, France? And if so, do you compare the French or feed the French ensembles into the UK ones to get an even better ensemble?
Well, that's called a super ensemble. So yes, they do that. So what's it that they do that? So you have the output from the European Centre, you have the output from the UK, you do it from France and Germany, America, and you can put all those together and treat them all as one huge ensemble and analyse those. They're called a super ensemble.
But how much overlap is there between the different areas?
Oh, well, no, globally, you see, the global ensemble is the whole globe. They do an ensemble for the whole globe.
But if you're in the UK office, are you working out the weather over Australia, say, in this detail? Or
Sometimes.
do you rely on getting Australian stuff in?
No. So, because you have these global models, in the UK, you can forecast for anywhere. You have the forecast for anywhere in the world.
So,
And they do that. So, one of the things you use these forecasts for is the routing of airplanes.
yeah.
You can do that anywhere. You have it for the routing of ships. You do it anywhere. You've got these global forecasts which allow you to do that. So any country can forecast for anywhere else if they've got a global model.
So do we have any more questions?
Yeah, I find that in the UK it's very changeable. So if you want to know if it's going to be sunny on the weekend, it's quite often rain.
Yes.
So what do you think? Are we missing some data, or
Ah,
why do you think that is?
Well,
Can I just repeat
Yeah.
that for the camera? In the UK, the forecasts are quite variable, and is there something that can be done to enhance that?
so the reason it's variable is because of two things. The latitude we are, and the fact we have the Atlantic Ocean to the west of us. So most weather systems, not all, most weather systems that affect the UK come from over the Atlantic. All right? And also, so even though you have observations, you don't have as many as over the land. So that makes the observations, by the way, it makes the weather very variable because we're on the east side of a large ocean. The other thing that causes it is that you have these things called the polar front. Now, the polar front is the interface between the polar air and the tropical air. And that's what a front is. That's why you see fronts. And the UK is just at the latitude where the polar front often is. So it moves to the north sometimes, and we're in warm air. It moves to the south, we're in the cold air. And it's because we're at that kind of latitude where the polar front, where you have this barrier between the warm tropical air and the cold polar air, is why the weather is so variable.
Another question? In the corner.
How does the Met Office use this data commercially, in terms of forecasting? Do they sell it to the BBC, ITV, newspapers?
Well, not the BBC, unfortunately. It lost the contract for the BBC. So the Met Office did the BBC forecast for a long time. In fact, Greg mentioned that I was head of London Weather Centre at one time, which I was actually responsible for the BBC weather broadcasts, the radio and television. And so that was done by the BBC, but they went out to contract. They went out to contract after the Met Office hadn't done it for a very long time. And another company, a commercial company, now does the forecast for the BBC, both radio and television. And so there's actually quite a vibrant commercial sector in meteorology. And how big it is, how vibrant it is, just depends upon local circumstances. So take America, for example. In America, most of the services that are provided to do with the weather are done by commercial companies. So what the National Weather Service does is it provides two things. It provides data, it provides the forecasts, and it provides warnings. But services for agriculture, for commerce, for building, for road transport, that's all done by commercial companies. So in the UK, it's a sort of mixture in the UK, so the Met Office does some commercial services, but also there's lots of services done in the UK by a company that is based in the Netherlands. So I was interviewing someone just this week about that, who does these services, based in Utrecht. And she was saying they do road surface forecasts in the winter for local authorities in the UK, because they got the contract. They won it off the Met Office. So these services, because you have global models, you can provide services from anywhere.
And another question in the back row.
Was it possible to forecast the extreme weather in Spain?
Sorry, I think
Was it possible to forecast the extreme weather in Spain?
Well, the camera, was it possible to forecast what happened in Spain?
Well, what I don't know is whether it was forecast. One of the problems with these extreme weather events is there's two issues. One is, was it forecast, right? And secondly is, was the information communicated to the people that needed it? And in Spain, I really don't know whether the National Weather Service issued timely warnings. It may have done, but often it's the local authority that is responsible for actually passing on and dealing with these local emergencies. So I'm sure that's going to sort of come out in the wash about where responsibility lies. Just tell you one thing that just come to mind, which is over sort of severe weather, which I thought was really interesting. Again, it's someone I was interviewing. And he was involved in a project somewhere in the Far East, I can't remember which country, Thailand or Vietnam, something like that. And he was providing advice about severe weather and this problem of how people respond to it. And he said to me, who do you, in a sort of remote area where there's going to be severe weather, who do you think is the most important person? Oh, I don't know. What's the answer? He said the school caretaker. Because the school is probably the only the school or the church is probably the only solidly built place where people could seek shelter. And so the most important thing is who can open the school so that people can be safe.
Do we have another question?
So satellites have made the southern hemisphere as accurate as the northern hemisphere, but we still use ground-based measurements as well.
Yes.
The southern hemisphere is still sparse relative to the north. So how important? It implies that the ground-based measurements are not actually very important.
They're less important. And that's happened with time because the satellite systems have got better at measuring different things. So when I was first involved in forecasting, so I joined the Met Office to do research, and they had a scheme whereby some people who joined to do research, they spent 18 months working as a forecaster. And so I spent 18 months doing shift work as a forecaster. And in those days, so this is the 1970s, all you had from the satellites was pictures, right? Cloud pictures, either infrared or visible, and a few of these radiant or the profiles from the polar orbiting satellites looking at infrared, and you just had one satellite like that, which I showed you. One single satellite doesn't actually cover very much. So what's changed is that they have loads and loads of satellites put up by different countries, measuring with their orbits, or not their orbits, but the bits that they're covering. With these polar orbiting, it only looks at a very narrow swathe of the Earth's atmosphere. And if you have a loss of these satellites, then every bit of the Earth's atmosphere is covered. And so in the early days of satellites, there was very little data coming from it. But as time went on, there's more and more, so more satellites, more sophisticated measurements. And then the surface observations became less and less important because things like I showed you with the atmospheric wind vectors, they could measure the wind, which you couldn't, that information wasn't there before. With a scatterometer, you can now measure the wind at the surface. That wasn't there before. And so the satellites, there's more and more of them, and the technology they carry, their ability to sound or to measure what's going on in the atmosphere has become greater and greater. So more and more is being measured, and that will continue in the future. And so you're quite right, the surface observations actually become less important.
Are they going to become redundant altogether?
No, I think it's unlikely because let's just take the UK. You'd like to be able to say the temperature at, I know, Heathrow was 30 degrees today. A satellite's not going to tell you that. So for local purposes, I think you carry on making surface observations. But nowadays, they're all done with automatic weather stations. You don't have people going out doing the measurement.
Redundant for forecasting.
Pardon?
Redundant for forecasting,
yeah,
as opposed to statistics.
Yeah.
So Mike, you had a question.
Okay, you mentioned supercomputers. When I used to work for government, they talked about CDC and Cray computers for Met Office.
Yes.
Do you still have individual supercomputers, or do you use a data centre for doing the computing?
For the Met Office, still has its own computer. But what's new is computers can be anywhere. So the European Centre for Mid-Range Weather Forecasting is based in Reading. I worked there for 3 years on secondment from the Met Office, and it had its supercomputer in the building in Reading. It's now in Bologna. The supercomputer can be anywhere now.
And it's an individual computer as opposed to, I don't know what you get in a data centre, but lots and lots of computers.
No, so the weather services tend to have their own computers. Yes. And I think probably one of the reasons that for the UK, for instance, is, rather than sharing with someone, is that the UK has its defence commitments. And so one of the very important services which the Met Office provides is to the defence. And what you don't want is, when you're doing your numerical forecast, for instance, is to be sharing your computer with other people.
Or relying on Amazon. Mike.
Can you say anything about short-term localised forecasts for sports? I'm thinking specifically of Formula One and cricket, 5-day cricket, and then Formula One weekend.
Right, so what you should do, that sounds rather presumptive. What I do, I play golf very badly, so I play golf once a week. Not now, I've hurt my knee. And if I'm unsure about the weather, I look at the radar. So on the Met Office website, just search for radar, and you'll get a radar picture of now, and you'll get a forecast, because what it does, it combines the radar from now with a model forecast, which actually then takes the radar now, radar rainfall, and merges that with what's coming out of the forecast model. So you then get a forecast radar picture, and that's what I do. It's you just click the button and it gives you the forecast, shows the time at the bottom, and that's what I do before I go and play golf. I have a look, and that's what they do. I don't know about cricket, so they do it at tennis. They look at the radar, because they have to decide whether to put the covers on the court, not when it starts raining, but before it starts raining. And I suspect the cricket grounds, they do that as well. The radar pictures are freely available on the Met Office. Look at the radar.
Do we have another question? That corner.
Going back then, how did they do forecasts in the 19th century? Was it more sophisticated than hanging seaweed out the window? Or?
Well, yes. So if you're talking before the subject of the Met Office, people just did their own forecast. You know, if you were a farmer and you lived somewhere for a long time, then you get to know the vagaries of your local area, especially if there are hills involved. So it may be, there's hills often, you get more rain on one side of the hill than another. You'd know that from experience. If you're at the coast, you'd know that, well, it's fog here, but I know it's going to be better a bit further inland. So you have that local knowledge. And so before the telegraph came along, before you could share observations, it was all based on what you could see and your limited local knowledge about what goes on in your area.
So does anybody else want to ask another one before Mike?
Another question, who supplies the military with their weather forecast? That's what you mean by the military. So you split this up. The Navy has its own service, its own Met Service, but it uses data from the Met Office, but it has a separate branch, and on ships they have their own officers. They're called METOCs, because they do both meteorology and oceanography. So they have those on the ships. In the Air Force, a lot of Air Force stations, RAF stations, not all of them now, but a lot of them have their own Met Office on site. And so they're manned by forecasters from the Met Office. And they interact very closely with the pilots. So the pilots will come into the forecast office and they get a briefing from the forecaster. Because for that, you need to know in detail about, are there going to be thunderstorms, what's the cloud base, and things like that. It's very important for flying. The Army tends to sort of ignore the weather, unless if they're just in general, but if they're operating at a particular place, a particular crisis, the Met Office has something called the Mobile Met Unit. And so these are civilian staff in the Met Office who have a commission, also have a commission in the army, and they go off to where the event is happening to provide local services for the military.
Okay, one for Mike now.
All right. Clear air turbulence,
Yes.
which can be very dangerous for passengers.
Yes.
Airplanes. Do you see the day when you might be able to forecast this more accurately?
Well, certainly try to forecast it, and also nowadays at least some aircraft have radar on board which can actually pick up clear air turbulence ahead of them. But the most important thing to avoid clear air turbulence is that from the forecast models you can create measures, statistical measures of clear air turbulence. So if you have a loss of shear, that sounds technical. If the wind varies very rapidly over a short area, that creates turbulence. It's like water running past each other. You get ripples, you get the clear air turbulence. And so you can, from the computer models, you can identify where clear air turbulence is likely to be. And that is one of the factors they take into account with routing the aircraft. So when you route the aircraft, you really want to do two things. You want to avoid clear air turbulence. You want to avoid going through the middle of a hurricane, for instance. But also you want to take advantage of the wind. So if you're flying to, in general, in the atmosphere, in the northern hemisphere, in the mid-latitudes, the air usually comes from west to east. Right, eventually it comes across the Atlantic. So if you're routing an aircraft, and you heard the jet stream, the aircraft fly at the sort of jet stream levels, about 10 kilometres, and the jet stream can be very large, be hundreds of kilometres per hour. So when you're routing the aircraft going west, you don't want it to be in a jet stream. You want it to be out the jet stream. If you're going from west to east, you get in the jet stream. You've got 100 kilometres per hour for nothing because the air's taking you. So forecasting clear air turbulence isn't perfect, but they do try to avoid it, and so increasingly radars are able to pick it out.
Thank you, Bob. So do we have a final question, perhaps? Come on then.
For the ensemble spread, can you quantify what sort of typical degree of variation you see? How much clustering is there, and how much are they going off on the tail?
It just varies, because, as I think I mentioned, sometimes all the ensembles group together and they all tell the same story. Sometimes, most often, but sometimes you can have 51 ensembles where everyone is different. And so I can't give an answer to your question. But what it means, this variation in this grouping of ensembles, is it indicates how much certainty, say, the BBC weather forecast, when they're doing the presenting, they can include in their presentation. Sometimes when all these ensembles show the same thing, you can be quite certain what there's going to be in 5 days' time. Sometimes with ensembles that are widely spread, you're struggling over 2 or 3 days.